So, I want to introduce the chairman of the session, Professor Obama. The chairman, what, they want it on, yeah. Okay, Shmuel, you have 45 minutes.
Okay, thank you. Avraham Neumann, who set up the program here, asked me to represent the history here. So that's what I'll try to do. So first part of the history, this is the paper 71, okay? Just, it is 71.
It's not 71/72?
No, it's 71.
That's 1 and 2, huh?
Here it is. Come on, I mean, yeah. He doesn't believe me. And to make it even more historical flavor, my chairman is Bob Aumann. So, really, I didn't quite know what to do exactly, but since I decided to speak about this result, which is, I didn't know that it will be mentioned so many times already. I'll speak about it mainly because, as you'll see later, there was some, it turns out to be applied and used and developed much further in the recent years, mainly actually by the French school. I will say more details about it. Okay, so so this is the first work, joint work with Jean-François, and I think it's his first work in game theory. This story, I will not speak too much of the folklore, maybe later in these days about this, what happened there, but I was a student, it was 1970, okay? The paper 71, but this was 1970. I was a student, a PhD student with Aumann, and he came back from a conference in Belgium, and he told me what he just told you here. He said, yeah, and there I found a smart young guy who I explained to him repeated games of incomplete information in 15 minutes, and he understood. So I invited him here, Jean-François. So that's what, when Jean-François arrived, 1970, first time to Israel, 24 years old, newly married, and we started working. And I will not really tell you how, because we tried things and so on, but let us go, because I want to have time to speak about recent things. So, so the situation, I'll start with this, although it was mentioned again, but just to put order here. So we're speaking of two players. That's the model of Aumann-Maschler. Two players. There are two sets, finite sets, K and L. Think of them as the type of player 1 and player 2, respectively. The pair of types is chosen by some probability distribution. Delta K, as usual, is the probability, a set of probabilities over K, and so for L. So the probabilities are known, and this is chosen at the beginning of the game. And the repeated games is played as follows. State 0, KL is chosen. Player 1 is informed of K, player 2 is informed of L. At stage T, as both players know the past history of the play, so it's full monitoring called later. Player 1 knowing K, player 2 knows L, and they choose an action, okay? Actually mixed action here. They choose mixed actions, and then the payoff is given by some matrices, matrices A superscript KL. The payoff of the finitely repeated games is average. The payoff of the infinite repeated games is a bit tricky. I mean, there are several ways to overcome this. There's a way to define some evaluation. I will speak more about this. Discount sum or lim sup or lim int for some Banach limit, or which was more adopted later, is to define the value without defining the payoff. I mean, to define what we call a uniform value. Okay, I'm not going to detail. So that was the situation. And Aumann Maschler had the following results. It was mentioned already, but let me repeat them. So 67, they spoke of the one-side incomplete information. So one typeset is just, it should not be empty, one single. Sorry, not empty, but single, okay? One type, okay? I just...
Curved brackets.
Then for this, they proved that the V infinity and the lim Vn and lim of V lambda. By the way, in this presentation, lambda will go to 0. That's with the 1 minus delta of the previous, okay? That went to 1, okay? Okay. And this is the operator that will play a big role here. The cav of u, this is a function of p. Cav is the least concave function that is greater or equal than u, okay? And this was a crucial operator. And then for the incomplete information on two sides, for the infinite game, they proved the following. Again, Aumann mentioned it this morning, which means that the lower value, the max mean, is cav of x. This is the min max is vex cav, vex with respect to q, cav with respect to p, and the issue of existence of the lim Vn was a problem. Again, since I mentioned historic notes, even this situation of not having a value for the infinite game, but the finite game, whether they can be limit, cannot be limit. I had a previous paper on before this work. There was first of all I had an example that showing that they can be such a game with V infinity non-existence and lim Vn exist. And then this was some hint that this may have a limit here. Yes?
What's the C in CAV? The AB is the average, right?
No. CAV is abbreviation from the word concave.
Oh, concave.
Concave. So this is the least concave function with respect to P. Okay, that's the used notation, so I didn't invent anything here. Okay, so that was the situation this was an open problem, as Bob said, and the first work with Jean-François was the following. For repeated games, zero-sum games with lack of information on both sides, we have that this does exist indeed. Lim Vn, which is the same as lim lambda goes to 0. This is a function of P and Q, which is characterized as follows. It is the unique solution of the following two functional equations. So you see phi here and here. Okay, so this is the maximum of u and phi. And maybe take the convexification of this and the concavification of the concavification with respect to p of the minimum. This also gives you phi. So these are two equations. Maybe I didn't emphasize enough. The u is the function. It was in previous slides. Yeah, it was here. This was what we call the non-revealing game. The non-revealing game, if imagine if none of the players would know his type, then they would play as if they play actually the average game here, okay? And this will be the value, okay? So this was the, I will get, there are several proofs to that. Even in the original paper, we have at least 3, 4 versions of the proof there. But I want to highlight just some ideas there. So first difficulty, and this was again a serious difficulty in the beginning, is that there is no straightforward recursive formula here. I mean, recursive formula you have when after 1 step or 2 steps you are in a similar situation that you were in the previous step. This is not the case in repeated games of incomplete information because the types are chosen once in the beginning of the game. Okay, so after 1 step, it is not true that we are in a new game of the same kind. So this, but to write to analyze a limit, we need something like that. I mean, even if really this is not the game, we need that we can use this some recursive formula. And this was really the first important point that had to be done. We had this lemma. What does this lemma say? That the game gamma n pq are the variables, has the same value as the following game. First, we play m stages, okay? Then the players tell their behavior strategy to the referee. Then the posterior probability PM, QM is told to both players, okay? And the referee, okay, they start playing this game. In other words, this becomes now really beginning of a new game, but with these values, okay? So it is as if a new game starting. Now, don't ask yourself why. This is just a mathematical tool. Don't ask why the referee should know and whether they will tell him the truth or all this. I'm describing a mathematical computation here, okay? Assume you do know it. Assume you don't know you know the behavior, and therefore you compute PM and QM, and then they start to play this game, okay? They played. They have a history of moves, actions. They play. That's m-1 history here. Okay. You can compute the posteriors. Okay.
They play and they tell
the referee.
Choose something and they tell their behavioral strategy.
Yeah.
Well, let's say first
they
behavioral strategy.
Yes, they tell it to the referee. Okay, very good.
They play, and then you compute the posterior.
Yes. Okay. Now from this, if you from this you get a real recursive formula. I mean, you have to use it again and again, and this is simpler to describe. The game gamma n has the same value as the game at which, at each stage m, the posteriors PM, QM is told to both players, and the pairs corresponding to that stage are determined by new lottery according to this posterior. Okay? Now, when you have this, you have a lot, because then you can write a recursive formula. And here is the recursive formula. The Vn plus 1 is the value of what game? The game in which in the first they choose mixed strategies here. This is the payoff for the first stage. And then they move to another game. Now, what is this? These things need explanation, although it's quite clear. X and Y are the mixed strategies. G is the payoff for the first stage. Xi here, this is actually the probability that I being played, okay? And this is the, okay, thank you. This is the probability that that J is played. Now, Pi and Pj are actually the posteriors before, but it's easier to think of them this way. This is the probability, the conditional probability on K given X and given that I was played, okay? And similarly for Yj. So we have a recursive formula. Now, with this recursive formula, then we, as I said, that. Excuse me?
What is X? X should be delta I to the K.
X, yes, you are right. That's a typo. That's a typo. Yes, yes. X is in delta I to the K. Yes, yes, yes. Thank you. Okay. I corrected 3 typos just about 10 minutes ago. But okay. So here is one way to go about it. Okay. To go from here to the proof. We prove that if player 1 can guarantee a certain function of PQ up to an epsilon, then he can also guarantee the curve over P, the vex over Q of the maximum of U and this F. Okay? And the dual thing. Very good. So here is why it works. We say at each stage, you play non-revealing. At each stage, you know the PM. Play non-revealing if the U is bigger than the F. Otherwise, go ahead and defend F of P and M. Okay? This will actually make you stay on the graph of the maximum of these two functions. Okay? So this gives us some inequality that, if you want, I didn't try to take here, but you'll see it later in different versions, that f of n plus 1 is greater or equal than the curve vex, the curve of the maximum of u and fn, things like that. Okay? And then we define this. I mean, we start, if you think of f, what player 1 can guarantee, okay? Then you start with something that he can guarantee certainly minus infinity. Player 2 can guarantee certainly this. We are speaking zero-sum games. And then you define this sequence, curve vex. Now, by the way, why the vex came in? Because you are not controlling what the other is doing. The other player is moving the Q, okay? So you cannot control. But as I said, it's not really a proof. I mean, okay, then you prove that Vn lower bar and Vn upper bar converge uniformly to this solution. In other words, there are two things there that we'll see it in a minute. I mean, these two sequences, one is decreasing and the other is increasing, and they converge. And another difficulty was there to prove that they're really equal. Okay, and finally the way to show that they are equal is to take the set in which one is strictly bigger than the other, and to prove that this, not strictly, I mean weakly bigger than the other, and sorry, strictly, but take the boundary, and the boundary of this cannot have an extreme point. Okay, it has no extreme point. Anyway, okay, so this is the proof. Yes. No, these are sequences of functions. Sequences of functions. This is a function. This is a function of PQ. This is a function of PQ. Take two functions, take the maximum, apply these two operators in this order. Okay? Okay, now, what...
In the lemma, it was random. But then you do
Yes.
try the max mean. Then
Yeah, you take the value. I mean, it's really. I want to get
the
that.
value of the
Oh, okay. Now, the extensions, first of all, some of the extensions were done by us. First extension is to go to the dependent case. So the probability on K across L should not be necessarily a product probability, or other way to say it is to take one type set, which now the type is two types, and there are two partitions here, okay? So there are partition of player 1, partition of player 2, probability distribution on K, and the matrices. This requires the generalization of the operators Cav and Vex, because we don't have square anymore, okay? We have to define, but this is done in more or less the way one would expect, okay? And this was important because this will be the link to what I will tell you later. We proved that this is true not to all continuous U. Continuous bounded U. Now, this function U originally was a value of a certain game. What I'm saying here is that it need not be a value of a game, okay? Any continuous function. That's why you can, this the beginning of understanding why this can be useful to other things, okay? So this was already in the original paper, okay? Later on, we went a bit further. We were asked by several people, this looks more like a mathematical programming thing. Game theory led to this, but we can think of it in a more way, in a more abstract way, detached from the game theory. So let us take P and Q to be compact and convex sets in Rk. So these not necessarily simplices, okay, respectively. U continuous real valued function on P cross Q. Okay, I'm back now to the, it's easier. I mean, you can do it, you can do the same with the dependent case, but to describe this, I'm back to the independent case, okay, to the product probability. Now, F is the set of all real valued functions. And look at the following pair of dual problems. Minimize F subject to F greater or equal than the Cav of Vex of max UF. Okay? F is here. The set of real. Huh? I think continuous. No. Wait a second. Continuous, yes, yes, yes. The dual problem is huh? Another typo. Ma? Okay, sorry. Yes, that's min. That's when you cut and paste. Okay, so this should be min, okay? These two dual problems of what we could prove is, first of all, that both problems have the same solution. Okay, they have solutions, and the solution is the same. Second, the common solution of problem 1 and 2 is also a simultaneous solution, and the only simultaneous solution of the following two equations. F equals Vex of the maximum, and F equals Cav of the minimum. You can see where it comes from, why it was made shorter here. One operator was not necessarily go back to this. What happens is that at the limit here, when you go with this sequence, there will be equality here, there will be equality here, and therefore this function is going, the limit is going to be both concave in P and yes, that's why we can get rid of this. Okay. The proof was purely analytic and made no mention, except in the introduction, that of game theoretical concepts or techniques. Okay, so this also maybe some reason why it was a little bit useful afterwards. Now, some years ago, this concept of MZ operator was, I think, introduced by Sylvain Sorin in a conference, in a day that was organized by François in Dauphine. In 2010, he gave a lecture. Sylvain Sorin gave a lecture. It's very, very hard. That's him, and that's the date, just to give you a tribute to the MZ formula. Now, he gave a lecture, and this was the first slide. He started, yes, I tried to make him print it or do something with it. So here is this is Aumann Maschler, AM, this is MZ, this is only the MZ71 that developed like a spider here. And I will not, definitely not give you even most of things here, but I will give you some ideas. Especially, I will try to tell you why this happened. That this operator or formula became useful elsewhere. Okay, and show you also where. I'll mention some of these works, not most of them, as I said. So what's the definition of the MZ operator, as Sylvain calls it? This is an operator that maps the continuous function, here it's continuous, the continuous functions on the cross product of the probability space on K and L to itself, okay? Defined by that MZ of U is the unique solution of equations E1 and E2 in the previous slide. Okay, not the previous one. Okay, that's the operator. Now, here is a slide from Laraki's presentations in Paris somewhere, and this is from his slide. Again, what you see here is what he's doing, and this is generalization, I think, is due to him, to Laraki. I think so, yes. What he does here is generalizing, actually, the discounting thing. Instead of discounting, you take just any weights here to the stages, okay? mu1 to mu, I call them weight, he calls them probability, okay? On the real numbers, and they sum up to 1. And the evaluation of the stream of payoffs is this, okay? And then we know that there is a value to this game. And the main question is the existence of this. This is generalization of the existence of lim v lambda, if you want, okay? As the supremum of this goes to 0, and okay, and the main tool, he just did the same thing, okay? The generalization, instead of lim vn, he has more now, okay?
G is the weighting factor?
What?
G.
G is the payoff at stage T. That's the stage payoff, okay? Mu is the time weight, okay? Mu is the time weight, okay? This is one generalization of Rida, Laraki. Now, I would like to explain why this became maybe one of the reasons that became relevant to other fields. I want you to recall what we had before, this recursive formula. If you look at this recursive formula, what do we have here? We have that, thank you. We have that we can think of PM, QM as a state variable. Okay? A state variable, and this looks very much like a stochastic game, okay? Where the state is moving in this space, okay? So this is, in principle, this recursive formula gives us the connection to, the natural connection to stochastic games, okay? On the other hand, what determines PM and QM? The strategy of player 1 determines this posterior, okay? So actually, player 1 controls PM. These are the beliefs of player 2 on his type. Think of it this way. PM is the belief of player 2 on the type of player 1. And it's in the control of player 1. Okay? Similarly, player 2 controls the beliefs of player 1 on his type. This is QM. So this really, now you see the bridge to differential games. Not differential because we need yet the continuity, but we have, think of, apart the discreteness here, that I will come to it in a minute, we have some situation in which a certain game develops in a way that player 1 controls this variable, and player 2 controls this, respectively. So this is the connection to differential games. Okay? And indeed, this was done. Now I'm showing you just the abstract of a very nice paper of Cardaliaguet, Laraki, and Sylvain Soran. And they do this. They do really the bridge, the connection between these two things. And what they do, what is needed more here is really this issue of discrete continuous. And this issue comes from, maybe before that, I should. No, I will come to that later. Okay. Another thing that is in this literature that involved the MZ operator is the following. This is something that again was what is called the operator approach. Again, it was developed, I'll say immediately, by whom? In the French school, as I call it. The Shapley stochastic game model is in a state space omega. We have this, okay? We have that for any f and any discounted factor lambda. We have this, which is what? Which is just the recursive formula, okay? This is the value of the game in which this is the first stage payoff, and this is the new state that develops after a certain x and y are played, okay? Or shortly, we have here an operator, which they call the Shapley operator, that transforms a function f to t of f, but this operator depends on lambda. So this is the recursive formula of the Shapley value. Now, and what is the result of Shapley is that the value v lambda is of the stochastic game is the only fixed point of this operator. V lambda equals t of lambda v lambda. Okay. This operator, as I said, it was originally introduced by Rida Laraki for the discounted game, okay, to study the discounted game based on the Shapley operator. So this is called the operator approach, And what is this operator approach is just based on actually the recursive formula, okay? And therefore, having a recursive formula was crucial in this. Now, by the recursive formula, we can use the Shapley operator, if we generalize this notion of Shapley operator to games with incomplete information. We have similar things here. We have that these are x in this time the k is there, y is this.
We don't see off.
Ah, yes.
To see off that item.
Okay.
Continuous function of that item.
No. No. This is not function. You are here?
F.
Oh, F, yes. F, yes. Okay. And what do we have here? We have that notice here. This is, think of x and y as the the strategy of the first stage. Mixed strategy depending on the type. So we have lambda times the payoff, 1 minus lambda. And here again, the notation is as usual, okay? Xi and yj are the total probability of playing I and j respectively. F of pi are the conditional posteriors that used to be m. And this is, again, we have an operator here of the same form. And again, the value, v lambda of pq, is the only fixed point of t lambda. Okay? And now this can be extended also to not necessarily to the discount factor, but to the other valuation. For instance, for the finite game, we have this type of relation: Vn equal t of 1 over n. This plays the role of the lambda and Vn minus 1. Okay. Now come the thing that I mentioned before, and it has to be explained. Again, I think this was introduced by Soran, if I'm not mistaken. I think it's already in his thesis. The idea is that that valuation, which is probability distribution over the positive integers, define a partition on 0, 1. How it's defined in the natural way: T0 is 0, Tn is the sum of the mu's up to that place. Okay? Now, this discrete game can be viewed as a game with continuous time on 0, 1, where the actions are constant on each of the intervals. Okay? Now you can write here recursive formulas, but the recursive formulas are with respect to what? With respect to this partition. With respect to this partition. The recursive formula gives you the following: the value sub p, this is the value of this game. Now, what is pi t1? Pi t1 is the normalization of on 0, 1 of the trace of the partition pi on the interval t1, 1. Okay, so you are at time t1, okay, and you want to write a recursive formula on 0, 1, value on 0, 1. So you normalize it again to 0, 1, exactly, and that's what you do. This is a recursive formula here, and you can have the value of a game starting at time tn, in other words, with mu n plus m is the value of gm, is given by this. Okay, rush then. So the stationarity gives you this type of formula, and by taking linear extension, you are now defining a value which depends on the partition of a continuous time on 0, 1. Okay? Now, why this is important? As I said, I mean, here now I really go quickly. This embedding of discrete game into continuous game enables using what they call in differential games viscosity solutions techniques used in differential games, and it was used. Second, evaluation of discrete game. The valuation of the discrete game can be viewed as a discretization of underlying continuous game. Okay? And this was really used for approximating the value of differential games using techniques and results from the discrete games. For example, I just give here a few examples. Pierre Cardelier, in his course on differential games, uses this formula, the MZ formula, and some elements of its proof to characterize the value of differential games with incomplete information. Another game, which I will go very briefly, was developed and defined by Rida Laraki, was, and this is the notion, the concept of splitting game is due to Laraki, but this is from a newer paper by Olyu Barton, 2012. And what is there, splitting game, you see, again, is another way to view these games of incomplete information. Because, as I said, PM is, what is PM? PM is the beliefs of player 2 on my type. Now, what can I do? How do I control this? By playing a certain mixed strategy. This mixed strategy will determine PM plus 1. Determine it in a way that its average will be PM. This is a martingale. So actually, I'm deciding how to split around the present value of PM, and that's the way. So the splitting game is. Let me, since I don't have much time, the splitting game is the following. Step 1. Now this notation is probability distribution with expectation this. So probability distribution with expectation this. Now the players can choose the splitting, okay? Can choose the splitting, and the stage payoff is U of XM, YM. If you look at it, it's just really stripping the story of incomplete information and leaving just the dynamics of the beliefs there, and the result of the result that in this paper is just this again. To see again all of a sudden these equations, and another thing I will go quickly is this is a PhD student of Cardelier in differential games, and she speaks of differential games here. Okay, differential games with incomplete information. Okay, so we have the same story with control of variables and so on, but the players have their private information, and their control sets and so on. I will not have time to again, you see the same setup, but they play differential game here. Okay, the types are chosen, and they are told to the player. They both play. They observe the control. This is the payoff. In differential game, you have two payoffs. This is the terminal payoff when it's finished, and this is what they call running payoff. Along the game, there's a payoff. So in any way, let me just show you the last of the theorem again. The value of this game with incomplete information, where the dynamics and the running payoff are not depending on the state. And there are some assumptions there under which this is the value. And this is the operator phi, the M, what Sylvain called the MZ operator, appears here in the solution of the value and appears here in the differential equation that plays. And finally, just a seminar that I missed last Sunday. Here is another generalization of the Mertens Zamir 71 thing. This Jérôme Bruno is sitting here with co-author. Generalize this, I think a very nice generalization is that the type of a player is not fixed, is moving according to Markov chain. And the result is similar, but I assume that among the main difficulty was really to detect what is the analog of the non-revealing, what is the U there, what is the non-revealing game there, not the revealing value, but my boss is saying that I finished. Okay, and thank you. Thank you.